So let's see if I can do this quickly and share those with everyone. A student emailed this problem and wasn't sure how to get the complex roots. So here we have this 6-degree polynomial. Notice that we have missing terms, so we need to take care of that as well. And we can start out, first of all, by using the rational root theorem or the rational zero theorem to determine the possible rational roots. So remember I shared with you that past students call it P's over Q's. Oops, I don't know what that is. P's over Q's. The P's are plus or minus 1, plus or minus 36, plus or minus 2, plus or minus 18, plus or minus 3, which is plus or minus 12, plus or minus 4, plus or minus 9, right? Because 4 times 9 is 36, plus or minus 5, nope, 6, and 6. And then that's where we're at. I'll rewrite this. Q's are plus or minus 1. So P's are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12, plus or minus 18, plus or minus, I forgot 9 in there, plus or minus 36, 1, 2, 3, 4, 6, 1, 2, 3, 4, 6, 12, 18, 9, and 36. Okay. And plus or minus 1s for the Q's, which means that all of these would just be all the different combinations of those numbers over 1. So our P's over Q's are, in fact, those numbers again. Okay? So I have to choose from those numbers to start factoring, right? And if I'm looking at this, I don't immediately see something that actually works right off the top of my head. So I want to do 1. I want to see if 1 works. So I'm going to substitute use the root for 1 and see if 1 is a root. That means my binomial is x minus 1, right? And so I'm going to divide that into this, since I'm choosing a binomial that is mono, meaning the lead coefficient of 1, then I can use synthetic division. So 1, which is going to be the case with all of this. So 1, and I have lead coefficient of 1, and I have to put in 0 terms, I'll remind you. X to the 5th, x cubed, and x are all missing. So we'll put those 0 terms in there, so that's 0. You have to when you're doing synthetic division. You can't do otherwise. Negative 6, 0, negative 31, and 0, and 36. Drop down the 1. 1 times 1 is 1. Add those two numbers, that's 1. 1 times 1 is 1. Add those two numbers is negative 5. 1 times negative 5 is negative 5. Add those two numbers, I get negative 5. 1 times negative 5 is negative 5, and I get negative 36, and it looks like it's going to work. 1 times negative 36 is negative 36. Add that to 0, I get negative 36 again. Multiply that times 1, and I get negative 36, and add that and get 0. Pow. The quotient that's left is x to the 5th plus x to the 4th minus 5x cubed minus 5x squared minus 36x minus 36. And that's that. And the number that's being multiplied by that, or the other factor, is this x minus 1. So I've just simplified or reduced my, simplified is the wrong term. I just reduced my 6-degree polynomial to be factors of a 1st degree and 5th degree polynomial. And so I'm going to start the process over again. This number is 36 and the lead coefficient is 1. This is still 36 and 1, so I still have the same P's over Q's. Okay? So these are still the ones I'm looking at. This is gonna be longer than I was thinking because of the 6th degree, but so we have to factor this down to the quadratic formula. That's always our goal. Get it down to the quadratic formula, or at least some parabola quadratic equation polynomial, so that we can either use the quadratic formula, factor, or otherwise. All right, when I'm looking at these numbers, look at this. I just changed the green yet. look at that term. Oh, blue. And this term. If I put a -1 in there, won't those two cancel? And if I put a -1 in these two x's, and same thing over here, so I'm going to use -1 as my next, which means I'm actually dividing x plus 1 into that 5th degree polynomial. So now I'm putting the lead coefficient down of 1, then -5, then -5, then -36, and -36. So I've changed the problem to trying to factor that. So I'm going to just scoot up here and do my synthetic division. Bring the 1 down, multiply, -1, add 0, -1, 0, -5. Multiply these two and I get 5. And add that and I get 0. That's going to be 0. And then -1 times -36 is positive 36. And when I add those, I get 0. Pow, it worked. So now I know my polynomial is x minus 1. That's from here. Then the new factor, x plus 1, which I just sorted out. And now this, as my quotient, is going to be x to the 4th plus 0x cubed minus 5x squared plus 0x minus 36. So my 5th degree polynomial becomes 4 because I factored it out and previously factored that out. When I multiply those out, they will still be the 6th degree polynomial all the way up here. Got to do it again. Still have my 36 and my 1, so my p's over q's are still this set of numbers. And 1 and -1 could work again. I'm not certain that that's going to be the case, so let's take a look at this. Yeah, I cannot discern from looking at those numbers, the -5, the 1, and the -36, what would actually work. Not easily anyway. 1 would definitely not work, of course. A -1 would not work as well. Yeah, I don't think 4 is going to work in any way, shape, or form either. That's got to just be a larger value. Some number squared times 5. Some number squared times 5. I don't know. I just kind of have to guess, I guess. 3 is in there. 12 is in there. 9 is in there. I guess I'm just going to go with 3. Let's see what happens. 3. We could do that. That's a nice trick. I don't know if I want to open that can of worms, though, for you. So 1, remember the 0 terms, -5, 0, and -36. The 0 terms exist up here, right? So that should be clear. Bring down the 1. 3 times 1 is 3. Add 9, 4, 12. 12. Ooh, it's going to work. 3 times 12 is 36. I got lucky. So now I have x minus 1, x plus 1. That's from up here. But this quartic turns into x minus 3 from here. And this quotient, x cubed plus 3x plus 4, 3x squared plus 4x plus 12. And now I think -3 is going to work. Yep, -3 is going to work. I can see that because -3 will be 27 here, and then this will be 27 positive. This will be negative, and then -3 times 4 is -12, and this is a plus 12. So those will cancel out or equal 0 as well. So 1, 3, 4, 12. Bring the 1 down, -3, 0, 0. Bring the 4 down, I get -12. That's 0. Boom. So now I know that x minus 1, x plus 1, x minus 3, and x plus 3 coming from that. And then I get x squared plus 4. And then here's the crux of the question that the student asked. How the heck do we get imaginary or complex numbers from that? And this is what we need to do. Now that we have a quadratic, we can do one of three things. We can factor, which this is factorable, but maybe not from your point of view. You could simply solve for x. Some of you wouldn't do that because you would, when you subtract 4 from both sides, right? Because you're going to set x squared plus 4 equal to 0, because that's what you're solving for, where this expression is equal to 0. If I subtract 4, I get x squared equals -4. Take the square root of both sides, and I get x equals plus or minus the square root of -4, which of course is plus or minus the square root of 4 times -1, which is plus or minus the square root of 4 times the square root of -1. But square root of 4 is 2, and square root of -1 is I. And so that's how we get that. Yeah, I don't know where that question is. So we get that. The other way to do that is take this. This is ax squared plus bx plus c equals 0. So a is equal to 1, b is equal to 0, and c is equal to 4. And substitute that into quadratic formula. I'm not going to do all this out. X is equal to -b plus or minus the square root of b squared minus 4ac, because the video is already long enough. Substitute these values in, calculate, you should get the same exact answer as this. So here are our factors: x minus 1, x plus 1, x minus 3, x plus 3, and x plus 2i, and x minus 2i. So that's the plus and minus. Okay? There are our factors. And recall the conjugate roots theorem, which this question is talking about, is these conjugate roots always come in pairs. The x plus 2i cannot exist without the x minus 2i in the context of polynomials being factored that have all real numbers for coefficients and constants. And that's it.